This is the screencast for section 6.4, example 6. Now in 5, we converted from polar form to rectangular, so in 6 we're going to do the vice versa. We first are going to start with a circle with center 3, 2, radius square root 13. So that'll help us confirm in polar mode that we got the right polar equation for this rectangular equation. In example 5, our goal was to get r cosine theta and or r sine theta and be able to plug in x or y. Now we're going to do the reverse, except there's some work we can do in the front that'll help make this a lot easier of a process. So first I'm going to actually square out the two quantities. Now I'm going to rearrange some things so that I have an easier situation to make sense of in terms of conversion. So I'm going to subtract 13 from both sides, and then if you remember from the example I showed you before, example 5, x squared plus y squared equals r squared, so that's an easy substitution to make. 6 times, and then x is r cosine theta, minus 4 times y is r sine theta, which will equal 0. So now I have to solve for r. And when equations are set equal to 0, the easiest way to solve is by factoring. So each of these have an r in common. So I'm going to factor out an r. So now either r equals 0 or r minus 6 cosine theta minus 4 sine theta equals 0. Well, if r equals 0, if our distance from the origin, r, is 0, that is the origin, which basically this point only tells us that the graph is going to go through the origin, which is good to know, but it doesn't necessarily help us with the polar form of this function. This, in fact, does help us. So now if I solve for r, I get my polar form, 6 cosine theta plus 4 sine theta, which we said was going to go through the origin, and we can find out when that is. We can find out when r equals 0. So I'll subtract 6 cosine theta from both sides. And now tangent is sine over cosine, so if I create sine over cosine by dividing both sides by cosine, and then I clear out the 4, divide both sides by 4, I am looking for an inverse tangent of -3/2. And that's where cosine is going, or where my function is going to equal 0, r is going to equal 0. So let's test that out on the graphing calculator. I used my window from 0 to 2 pi, but actually, now that I'm thinking about it, inverse tangent has a range from -pi/2 to pi/2. So I want to make sure that my x min goes beyond 0. So I'm going to make that go from -pi and then instead to pi. Now let's graph. So there's my circle. It definitely looks like it has center 3, 2. I'm going to hit trace. And I want to make sure that maybe the point inverse tangent of -3/2, 0 is on there. Well, it would be 0, inverse tangent of -3/2. So I'm going to hit trace, and then I'm going to put in inverse tangent of -3/2, which does in fact have an r value of 0. So in polar form, the circle whose center is 3, 2 and radius square root 13 has the equation r equals 6 cosine theta plus 4 sine theta. And I double checked by making sure that r does in fact equal 0 at some point on the graph. Turns out it was the inverse tangent of -3/2. The now try problem number 43 looks pretty simple, and if you remember from previous examples, you might be able to convert this vertical line at x equals 2 right off the bat, but showing your work is definitely part of the process. So you need to be able to show and demonstrate that you know how to get through this process. So first I'm going to convert x into r cosine theta equals 2. So that means that r equals 2 over cosine theta, which that is just r equals 2 secant theta. Check that on my graphing calculator, and by using 2 over cosine theta as my r1, I was able to get, in fact, a vertical line at x equals 2.